I am Jim Kane, Chief Technology Officer at Waldo Air, located in Santa Rosa Beach, Florida. We are discussing our poster presented at the 2025 Communication Theory Workshop in Murano, Italy. The poster is titled Direct RF Subsampling of Multicarrier Waveforms. To the right, we show the implementation of orthogonal frequency division multiplexing, or OFDM, that has been a digital communication standard for 50 years. The transmitter uses the inverse FFT to generate real and imaginary time samples that are upconverted to the carrier by an IQ mixer and then summed. After transmission through the wireless channel, the receiver's IQ mixer separates the signal back into real and imaginary components, then low-pass filters both I and Q channels to remove the 2x carrier parasitic noise. The receiver's two baseband channels are digitized with separate ADCs and input to the FFT. The FFT output is the AB coefficients that contain the QAM data. Although ADCs have increased in sampling capability by over 1,000 times in the last 25 years, the receiver's sampling must occur at the signal bandwidth because of the FFT. So, for a 20 megahertz information bandwidth, the FFT must process samples at 20 megahertz, even though available chips can sample 1,000 times faster. The research presented here replaces OFDM's receiver processing with a single ADC and the Kalman filter. Why would we modify the elegant and time-proven OFDM mechanization? We have listed a few benefits here. First, the Kalman filter processing is recursive versus FFT's batch process. That is, the digital samples are processed as they are received, as opposed to awaiting collection of all samples across a single time. The Kalman filter sample rate is independent of the subcarrier frequency spacing, and the subcarrier frequencies can be spaced arbitrarily. Direct RF sampling methods are of interest because of availability of fast ADC sampling rates. But implementation of direct RF methods are hindered by the digital processing requirement at these extreme speeds. That's where subsampling at well below the carrier will enable practical commercial implementations of direct RF radio. This uses the bandwidth of the fast ADCs, but the slower sampling reduces the processing demands. Peak-to-average power ratio, or PAPR, is a key known OFDM weakness. The transmitted signal has wide dynamic range that must be digitized with high precision. The Kalman filter allows skipping all high measurements that are outside a threshold without impact on performance. Moreover, and possibly the most significant benefit, per sample processing allows a characterization of the wireless channel. The Kalman filter predicts the next measurement and compares this predicted measurement to the actual measurement to form what is called the residual. The standard deviation of this residual is also computed internal to the Kalman filter. So we can determine by residual analysis if the waveform model is correct. A good example is multipath corruption, where reflected delayed waves interact with the direct path waves. The Kalman filter can detect this corruption in the residual and take corrective actions on subsequent symbols. Consider the use of AI methods that recognize patterns within these residuals to detect specific channel-induced effects. Finally, the new approach replaces all receiver IQ processing with a single channel ADC, offering a simpler system design with fewer opportunities for self-induced error. The key to Kalman filter application is the multicarrier system math model. FFT's waveform model must begin at DC and the subcarriers must be spaced at a constant interval. We show here the FFT subcarrier model at baseband in its exponential form, with complex A and B terms for each subcarrier tone. If we expand the OFDM mixer math, we get the original spaced frequency terms, but with the frequencies offset by the carrier. This is the real signal that must be sampled and processed by the Kalman filter, so that the new receiver design must work with legacy communication systems. Now let's look at the Kalman filter estimator in detail. The Kalman filter is fully defined by its underlying math model, and this model must be cast into a state space form. Each subcarrier can be perfectly represented by a second-order differential equation as shown here for the nth subcarrier. The differential equation has a solution that includes OFDM's transmitted waveform with the carrier offset included in the model. The differential equation model also allows for arbitrary frequencies on each subcarrier. Think, for example, cognitive radio, where we adaptively place subcarriers at opportune locations within the spectrum. Or we can separately treat the pilot tones with their pre-assigned A and B values. The total subcarrier dynamic model will be comprised of n of these second-order differential equations. Not shown on the poster, we can choose a single subcarrier frequency and normalize all frequencies to the single or carrier frequency, so that all frequencies are very close to 1. With this normalization, the independent variable, that is time, for each subcarrier becomes carrier cycles. Thus, a single Kalman filter algorithm applies for all carrier frequencies. The Kalman filter state vector is a concatenation of the signal and signal rate for all subcarriers. So the state vector has length 2n. The measurement matrix H models the summation of the subcarrier signals and thus is just alternating ones and zeros as shown. Given the waveform model, the Kalman filter algorithm becomes fully defined. The components of this algorithm are shown to the right. We have the state dynamics equation with the system matrix F being block diagonal with 2x2 matrices along the diagonal. This simplifies the computation of the transition matrix, which transforms the state vector from one digital sample to the next. The covariance matrix P propagation step is simplified due to the block diagonal transition matrix. The Kalman gain K computation is shown, and this computed variable as a function of time is the only variable that must be stored for real-time use. Only the state propagation to the next measurement and the state update at that measurement are computed in real time. Because the frequency normalization to 1 and the use of carrier cycles to replace time, all computations can be performed using fixed point arithmetic. Also note that the sample interval, or delta t in cycles, enters only in the computation of the transition matrix. The delta t will be less than 1 cycle for sampling faster than the carrier frequency, or may be greater than 1 cycle for subsampling. For the simulation case studies below, we will use a sample interval of 10.2 carrier cycles. Not shown on the poster, the Kalman filter estimates the signal and signal rate states for each subcarrier. But we want estimates of A and B. Fortunately, this transformation is linear, although time varying, And so the A and B estimate terms can be readily mapped from the signal and signal rate. This is also true for the covariance matrix of the A and B terms that are of interest. A Monte Carlo simulation was developed for the multi-carrier communication system. We used 64 subcarriers with QPSK modulation formed from A and B values randomly selected from +1 and -1. For the case as shown, we used a white noise with standard deviation of 1 and a receiver subsample time of 10.2 carrier cycles. The normalized subcarrier frequencies represent a 20 megahertz bandwidth beginning at 2400 megahertz. The OFDM symbol time, ignoring the cyclic prefix, is 1 over the frequency separation, or 7,680 carrier cycles. The simulation covers the OFDM symbol time plus an additional 25%. The top pane to the right shows a standard deviation of all A and B values for all 64 subcarriers, a total of 128 time history values. Interestingly, the sigma A and sigma B values are identical at all times. Moreover, the two innermost subcarriers have identical sigma A and sigma B values, as do A and B pairs that occur moving away from these inner subcarriers. So there are, in fact, only 32 unique sigma time histories that illustrate the convergence performance. We also see that the outermost edge subcarriers that have less neighbor interference converge faster than inner subcarriers. The Kalman filter is an optimal result, given that the model is accurate. We see the Kalman filter converges to its final result faster than OFDM's symbol time, which directly translates to throughput improvement. The second pane shows the predicted measurement and actual measurement from the Monte Carlo simulation. This shows the spiky nature of the OFDM signal and suggests the requirement for high-resolution sampling. The difference in the red and blue curves on the second pane form the residual that is plotted on the third pane. The third pane also shows the plus and minus residual standard deviations as the red lines. For a well-behaved Kalman filter, residuals are white, and 67% of residuals are contained within the standard deviation bounds. The fourth pane shows an example of an A-B estimate time history for the innermost and outermost subcarriers. As suggested by the standard deviations on the first pane, the outer subcarriers converge faster than inner subcarriers. The last section of the poster shows several examples illustrating further Kalman filter features. The first example is residual analysis. The Kalman filter residuals are well known to be useful for assessing the system model. In fact, there is a subset of modern estimation theory known as system identification, where residual analysis selects the best system model from multiple candidates. The chart to the right shows the Kalman filter residual process when a reflected multipath wave is coherently summed with a direct path wave early in the symbol processing. As can be seen, this occurrence can be readily detected and the Kalman filter restarted. This adaptive multipath treatment may offer benefits over traditional fixed cyclic prefix. Next, we look at PAPR. We noted above that Kalman filter subsampling is established by setting the sample time in the transition matrix computation, 10.2 carrier cycles in this case. The Kalman filter allows non-equally spaced time samples, which also covers skipping measurements. This is done by simply omitting the state update at the measurement, but continuing to perform the state propagation step. For the case shown, the Kalman filter will have 7,680 divided by 10.2, or 753 digital samples across an OFDM symbol time. The FFT, on the other hand, would have processed only 64 real and 64 imaginary digital samples across this same symbol time. Thus, the Kalman filter will have significant excess data samples. On the pane to the right, we set a measurement threshold of 15 and skipped all measurements outside this value. The estimation performance for this case was not noticeably impacted by skipping over 5% of the measurements. As a final case study, we look at taking advantage of known A and B quantization. Quam modulation results in quantized A and B values, with QPSK selected from plus and minus 1. If we stop the estimation for a subcarrier as its sigma drops below 0.33 or 6 sigma, then we will introduce less than 3.4 errors per million symbols. This logic is mechanized in the Kalman filter by zeroing the appropriate term in the H matrix. The pane to the right shows the symbol time improvement from performing this early A-B assignment step. As the outer symbol pairs are dropped from estimation, their neighbor inner subcarriers will become the outermost subcarriers, thus accelerating their convergence. The faster convergence will result in improved throughput. What's next for our development direction? We are working towards a hardware demo of the new approach and will emphasize channel characterization. We are also working on a high-Q digital bandpass filter that will be integrated with the demodulation filter. This will both reject neighbor communication channels and will allow data population of edge subcarriers, also making use of subsampling. Finally, any phase shift key modulation will produce subcarriers with fixed amplitude so that the A and B values are perfectly correlated. This correlation can be enforced by properly setting values in the initial covariance matrix with no change in the Kalman filter algorithm. Evidence suggests that this will reduce the convergent time by 1/2, which will result in significant throughput improvement. We conclude the poster discussion with a request for collaboration. Waldo Air seeks collaboration in independent verification of the results presented here. We also seek collaboration in development of real-time demonstrations using actual transmit-receive hardware.